Welcome to the Getting Started with GeoStudio video series. This tutorial guides new users through the basics of creating a simple solute transfer analysis in CTRAN-W. This video will cover how to set up the properties of a CTRAN-W analysis in the definition view, use the Solve Manager to solve the numerical analysis, interpret the solved analysis in Results view, and view and print the analysis in page layout mode. The project definition involves selecting the basic analysis properties, drawing the model geometry, creating and assigning material properties, and defining the boundary and initial conditions. This tutorial considers advection dispersion solute transport from a contaminated storage pond. A steady-state seepage analysis provides the water transfer results given the pond near a valley slope. Mass is allowed to exit the domain along the slope and valley bottom. The particle tracking functionality will be used to examine how individual particles may move through the soil over time. We will begin on the GeoStudio Start page. Here you can create a new project, open an existing project, or click on the appropriate links to view the examples, tutorial videos, or engineering books for each GeoStudio product available on the GeoSlope website. When creating a new project, you can select the default units and project page size from a range of standard sizes. After clicking on the New button, I will select the metric units with a letter-sized page and create an analysis. Once the new project is created, the Define Analyses window opens, where we can edit the analysis tree title, specify the author, or add comments for future viewers. First, we will add a steady-state SEEP-W analysis to the analysis tree, followed by a transient solute CTRAN-W analysis. We may edit the analyses names, change the analysis type, or add a description about the analysis. In the Physics tab, we can select additional mass or heat transfer processes. For the SEEP-W analysis, we will only model groundwater flow due to pressure and gravity-driven gradients. However, we wish to model advection dispersion with water transfer in the CTRAN-W analysis, so we will select this additional physical process. Under the Solute tab, we may define the initial solute concentration throughout the domain by selecting the parent analysis or another GeoStudio analysis, or a spatial function. In this case, we will leave the initial concentration as undefined because we will specify an activation concentration in the material properties. This tab also contains the convergence criteria. Here we can change the maximum number of iterations and the iteration comparison criteria. A separate tutorial video is available with a detailed description of the convergence inputs. More information on these criteria is also provided in the online help. Under the Water tab, we must specify a water transfer analysis. Water transfer results are required for diffusion-only problems as the volumetric water content is needed to calculate the effective coefficient of diffusion. Water transfer results are also required for advection dispersion contaminant transfer analyses like this one. Let us select the parent analysis from the drop-down menu. The Settings tab allows for the selection of the analysis dimensions, which we will leave as 2-dimensional. Under the Time tab, we can change the time steps and duration of transient analyses. Let us set the duration to 2,500 days with 50 time steps. We are currently in the definition view of our analysis. The red and green lines in the model space represent the X and Y axes respectively, and the grid is activated. Both of these may be turned off by going to View Grid. The grid spacing and Snap to Grid option may also be modified here. The base units of the analysis are found under View Units. Both the base units and the derived units may be modified. However, we will use the default units for this analysis. The zoom options along the bottom bar of the screen provide various options for adjusting the analysis view. We can also go to View, Zoom to change the display scale and current zoom percentage, or zoom to the extents of the model domain. We can add axes to the working area to help visualize the drawing extents of our domain. Under Sketch Axes, we can specify the titles for each axis, as well as the X and Y axes extents. The X-axis extent will be 24 meters, and the Y-axis extent will be 11 meters. You can also modify the axis increments by toggling off the Auto Increment Size button and changing the increment size for each axis. We may also modify the reference scale under Define Scale. Let us change the reference scale to 1:100. This will ensure that 12-point font is sized correctly when zoomed in at 100%. Let us now set up the domain geometry. There are several methods for drawing the model domain. First of all, we may import regions from DWG or DXF files or from other GeoStudio files by going to File, Import Regions. We may also import a drawing under Sketch Pictures, scale the drawing to the model domain, and use it as a reference for creating the desired regions. Alternatively, we can copy point coordinates from another GeoStudio file or from spreadsheet software like Microsoft Excel and paste them into the Define Points window. Finally, we can draw regions by going to Draw Regions. Let us use this last option for defining our geometry. In the Draw Regions window, ensure the polygonal region type is selected. Points are automatically generated when we click on the working area, and lines are created between these points. We may also enter point coordinates in the coordinate entry box at the bottom of the window. To stop the Draw Regions command, click the right mouse button or press Escape. Additional points can be added to the domain if required. We will add a point along the side of the pond at the reservoir water level. This point ensures that the boundary condition associated with the pond is applied to the appropriate portions of the domain. The sketch tools may be used to draw geometric shapes to help us visualize various aspects of our problem. These sketches are not included in the domain or the analysis and can be moved, modified, or deleted using the Modify Objects command. After defining the model geometry, the next step is to create and assign the material properties. To establish the material, we will go to Define Materials. We will click on the Add button to create a new material and give this material a name. Let us define the bulk diffusion coefficient function by clicking on the ellipses button, adding a new function, giving this function a name, and selecting the spline data point function type. We can create the function by selecting a dataset, adding data points into the entry boxes at the bottom of the window, or by pasting data points into this window from a spreadsheet. I previously copied 2 columns of data points from a spreadsheet, which I will now paste into this window. After closing the Define Diffusion function dialog, I will select this function from the drop-down menu. We will assume that the contaminant present in the pond does not undergo adsorption or decay, so we will leave these entries blank. Let us specify a dry density of 1,720 kilograms per meter cubed, a longitudinal dispersivity of 2 meters, and a transverse dispersivity of 1 meter. In this case, the dry density could have been left as 0 because we are not modeling adsorption. Finally, we will assume that the initial contaminant concentration throughout the domain is 0 grams per meter cubed. To do so, select the Activation Concentration option, which is automatically set to 0. We are now finished defining the solute transfer material properties, so we can close this window. Now we must define the hydraulic material properties for the seepage analysis. Click on the steady state seepage analysis in the analysis tree and go to Define Materials. Ensure the silt material is selected and choose the Saturated, Unsaturated Material model from the drop-down menu. We will use the estimation routine for both the volumetric water content and hydraulic conductivity functions. First, we will click on the ellipses button beside the volumetric water content function, add a new function, give it a name, and select the volumetric water content data point function type. Click on the Estimate button, enter a saturated water content of 0.35, and choose the silt sample material. After pressing OK, the estimated function appears in the graph window, and the corresponding data points are listed in the data table. The coefficient of compressibility will be set to 1 times 10 to the negative 4 per kPa. We will now close the function definition window and select the develop function from the volumetric water content function drop-down menu. Now, let us specify the hydraulic conductivity function by clicking on the ellipses button, adding a new function, changing its name, and selecting the data point function type. Again, we will estimate the function. Select the Van Gunsten estimation method and choose the volumetric water content function we just defined from the drop-down menu. We will set the saturated hydraulic conductivity to 1.2 times 10 to the negative 7 meters per second, and the residual water content to 0.05. The material definition is complete, so we can close the Define Materials window. Now we will add the material to our domain by going to Draw Materials, selecting the material, checking the option Apply to Multiple Analyses, selecting both the steady-state seepage analysis and transient solute transfer analysis, and clicking on the region. This allows us to apply the material properties to both analyses at once. Creating and assigning boundary conditions is very similar to creating and assigning material properties. When in the steady-state seepage analysis, go to Define Boundary Conditions. There are two boundary conditions already defined, the zero pressure boundary condition and the drainage or potential seepage phase boundary condition. In addition, we will need a boundary condition to represent the water level in the pond. We will set the new boundary condition to a constant head of 10.25 meters. We can change the color of the boundary condition by clicking on the Color Set button while the item is active. Let us now apply these boundary conditions in the steady-state seepage analysis by opening the Draw Boundary Conditions window. We will apply the zero pressure boundary condition to the valley floor, the drainage boundary condition to the slope, and the pond boundary condition to the two lines where the pond water level influences the domain. Now we must define the boundary conditions for the transient solute transfer analysis. In the Define Boundary Conditions window, let us add a new boundary condition to represent the pond concentration. We will set a constant solute concentration of 10 grams per meter cubed for the pond boundary condition and change its color. Next, let us add a free exit boundary condition by creating another boundary condition and selecting the type Solute Free Exit Mass Flux. We can also change the color of this boundary condition. To apply the created boundary conditions to the model domain, open the Draw Boundary Conditions window. Select the pond concentration boundary condition and apply it to the two lines influenced by the presence of the pond. Then apply the free exit boundary condition to the valley slope and floor. The last step of developing a numerical analysis is to view the finite element mesh by going to Draw Mesh Properties. Here we can see that the default mesh is set to have an approximate global element size of 4 meters. We will create a finer discretization for the global mesh by changing this value to 0.5 meters. Mesh constraints can also be applied to individual regions, lines, or points. Finally, we wish to add particles to the solute transfer analysis to simulate how individual particles would move through the soil over time. To do so, go to Draw Particles and click on the points you wish the particle to begin at. Now we will ensure the analysis is activated in the Solve Manager window and solve the analysis by clicking on the Start button. Once solved, the window will automatically change to the results view. By default, the water and mass flux vectors appear once the analysis solves. For better viewing of the mass flux vectors, we can turn off the water vectors by going to Draw Vectors and deselecting the Water Flux option. Visualization of the mass flux vectors can also be modified in the Draw Vectors window. Here you can change the vector color, maximum vector length, or the vector magnification. We can add contours to the domain by selecting a contour type from the drop-down menu. We may modify the contour options by clicking on the Draw Contours button. In this window, we can add a new contour, change the contour increments, modify the contour color scheme, and add or remove the legend. Contour labels may be added by selecting Draw Contour Labels and clicking on the desired contour. The label disappears when we click on the contour a second time. The blue shaded area represents the pond water level. The Results Times window provides a list of the solved time steps, allowing you to view the results for each time step. As we click through the time steps, we can see how the position of each of the defined particles changes over time. The particles and concentration contours indicate a general spreading in the mass within the system over time. We can add a line depicting the water table by going to Draw Isolines, adding a new ISO line, and selecting the water pressure option drawn at a value of 0 kPa. In this window, we may also create an ISO line representing a specific concentration value. For example, if we wish to view where the solute concentration is 2 grams per meter cubed and how this progresses over time, we will specify this value in a new concentration ISO line. Note that only one ISO line may be viewed at a time. We can also choose what items are activated in the Results window using the View Preferences toolbar along the right side of the screen. Here we can toggle results information on or off. There are other options available for viewing result information. View Object Information provides information on each geometry item, such as the boundary condition applied to a line or the mesh properties of a region. View Result Information provides details for a node, Gauss region, and so forth. This information includes coordinates, pore pressure parameters, water and mass flow parameters, material properties, and convergence results, which can be useful when evaluating or comparing results from specific nodes within the domain. A report of the analysis may be generated by going to View Report. The report is an HTML file summarizing the input data, domain geometry, and other information from the analysis. The Draw Graph window offers a wide range of options for plotting the model results. A plot of the hydraulic conductivity over matrix suction has automatically been generated. This plot demonstrates that convergence was reached for the water transfer analysis, as the inputted hydraulic conductivity function, represented by the red squares, matches the plot of the computed hydraulic conductivity from the second last iteration with the final pore water pressures computed at each Gauss point, in blue. To create a new graph of the concentration profile below the pond, we will press the Add button, name this plot, and select Concentration versus Y from the drop-down menus. We will then click on Set Locations to choose which nodes to plot the results from. If we change the Select option to Geometry Items, we can choose a region, line, or point. Select the nodes along the left side of the domain by clicking on this line. Back in the Draw Graph window, we can change the visualization of our graph by selecting the More button and going to Options. Here we can customize the labels, change the scale of each axis, rotate the graph 90 degrees, add or remove the legend, or change the line style. We will rotate the graph 90 degrees so the Y values are plotted on the Y-axis. Next, let us create a graph for the cumulative mass leaving the domain along the free exit boundary. We will select the nodes using the Geometry Items option and by holding down the Control button so we can select both the lines representing the valley slope and floor. Back in the Draw Graph window, select the following drop-down options: Mass Flow, Cumulative Solute Mass, versus all time steps. To plot the total mass leaving the selected lines, sum the Y versus average X values. The negative values indicate that mass is leaving the domain. At first, minimal mass leaves the domain, but this increases over time. The More button also provides the following options: to copy the graph as an image so it can be pasted as a picture in another program, to copy the graph data as tab delimited columns which can be pasted into other software like Microsoft Excel, or to export the data to a comma delimited file. If at any time you are unsure in your understanding of a dialog box, select the Help tab or press F1 on your keyboard to access the online help. If at any time you would like to view the engineering book for the product you are using and do not want to return to the GeoStudio Start page, you can simply click on the Home button in the online help. Once we are finished interpreting the results, we can view the Page Layout layer to set up the printing properties of the project file. The Page Layout toolbar allows for the selection of the paper's size, margins, and orientation, the portion of the page in which the model appears, called the viewport, and the positioning and size of the model within the viewport. We may also create, modify, or import a printing template. A basic template was created when we selected the page size while setting up our project file at the beginning of this tutorial. That concludes our Getting Started with CTRAN W tutorial video. Please see the online help, supporting documentation for CTRAN W, and other tutorial videos available on the GeoSlope website for more information. Thank you for watching.